So just to recap for you, we're going to pick up where we left off in Chapter 7. We started out with looking at the structure of a given nerve cell as well as location of these different pumps and channels. And we even started talking about the role of gated channels and how they contribute to the different polarity changes of the cell. We talked about depolarization, repolarization, and hyperpolarization. And so if we go back to our objectives, what we're going to now do is pick up and talk about a gradient potential and how our gradient potentials can sum by temporal or spatial summation, and how they can be used to generate an action potential in a given nerve cell. And then we'll also review the ions which contribute to the phases of an action potential, which we became familiar with in lab last week in the handout that you guys are turning in today as well. We will also talk about the conduction of an action potential along those cells which are myelinated and those are not. Last time we said, well, myelin is or is not present. We're going to add, well, how does it actually help? And then if we have time, we'll talk about the role of a refractory period and what the heck that is. Just to recap for you where we left off on Tuesday or the other day, was looking at a cell membrane, a nerve cell membrane. We acknowledged that the regular membrane, if you will, is a phospholipid bilayer, but there's a whole bunch of sodium-potassium pumps and leak channels for sodium and leak channels for potassium. We also concluded that the role of these things is to allow the cells to maintain what? Resting membrane potential. In other words, the cell is not electrically neutral, but it has a charge. And what is the charge of a cell at rest? Negative 70 millivolts. And we try to quantitate it outside of the cell. The sodium has a greater concentration of about 150 millimoles versus on the inside at about 15 millimoles. So you can quantitate the actual difference. And it's nearly the reverse for potassium. Potassium is in greatest concentration inside of a nerve cell, about 150 millimoles. In contrast, extracellularly at about 5 millimoles. Are you able to kind of appreciate the difference that exists at this point? Sodium's in greater concentration where? Outside of the cell and less inside. And it's reversed for potassium. Hopefully you should be able to take away now, there is a difference because why? The cell creates a difference, why?
To create a gradient.
To create a gradient so it can be used. So this gradient exists so that this nerve cell can use the gradient. And what we're going to call now graded potentials in action. So before we move on, what questions do you have about this establishment of the resting membrane potential, the role of the pump, and the role of the leak channel? All right, good with that? Wonderful. And so on Tuesday, we did talk about some different terminology, but let's just review here. We said a nerve cell maintains resting membrane potential. We said it does maintain a charge of about negative 70 millivolts. The word resting might be a bit misleading. The word resting simply means what?
To have an action potential.
It's
not receiving a stimulus.
No stimulus is present. And certainly it's not going to be generating an action potential nor a graded potential. But it's kind of at its steady state, ready to receive a stimulus. Therefore, they use the employment term rest. However, we do know that once that gradient is established, we can use it to change the polarity. We learned that if a cell's polarity becomes less negative, we would say it's depolarizing. So depolarization implies that a nerve cell membrane can become less negative than it was at. Your book uses the phrase more positive. I just wanted to caution you using the word more positive. Yes, but I think it might be less confusing if you just say less negative because it doesn't give you the scale of depolarization, the quantity. So a nerve cell may depolarize. It may also what? After depolarization, it could repolarize. During repolarization, the cell is regaining what? In which potential? The resting membrane potential. Which ion contributes to repolarization?
Potassium.
Potassium moving
In.
out of the cell. Potassium moving out of the cell, and you could say down into electrochemical gradient, because we said at rest, potassium's in greater concentration in the cell, so we open up a gate, potassium's going to flow out of the cell, causing the cell to repolarize.
You said down its gradient?
Yes. Through any gated channel, sodium gated channel, potassium gated channel, calcium gated channel, fill in the blank. An ion will move, yes, down its concentration gradient. Or you say electrochemical gradient. Let's restate that. During a period of repolarization, which ion? Potassium is moving out of the cell, down its electrochemical gradient, causing the cell to become
More negative.
more negative. I want to be careful saying that because I don't want you to confuse with the next thing, but you're correct. So I think an easier way to not confuse you is to say regaining resting membrane potential. Going back towards resting membrane potential, but it is technically going back towards a more negative state. So if potassium moves out of the cell is repolarizing. Which ion contributes to depolarization?
Sodium.
Sodium moving into the cell. Y'all are gonna mess with me now. During depolarization, sodium moves into the cell. And we know that may be through gated, mechanically gated, voltage gated, chemically gated, thermally gated, whatever. If sodium's moving more in, the cell is going to depolarize. We also concluded that cells can undershoot the resting membrane potential. What is that phase called? Hyperpolarization. In hyperpolarization, the polarity is more negative than it was at rest. Which ion can contribute to hyperpolarization? Potassium moving out of the cell. Potassium moving out of the cell. Extra potassium moving out of the cell. So it's at rest, and then we open up gated potassium channels and undershoot it.
Would that be against its gradient?
No.
Okay.
It's still moving down its concentration gradient. So potassium, we can use the word efflux. Potassium flowing out of the cell may cause the cell to hyperpolarize. If it was at rest, and we open up a voltage-gated potassium channel, it may hyperpolarize. I would like for you to add another ion which can contribute to hyperpolarization. We won't see it in play during the action potential, but we may see it in another scenario. So another ion which can contribute to hyperpolarization is called chloride ion. What charge does chloride ion have? Negatively charged. So if I open up a gated chloride ion channel and then it causes the cell to hyperpolarize, which fluid would chloride move into the cell. And fluoride ion diffuses in, it can lead to hyperpolarization. I'm going to put a star here because this is, fluoride ion won't cause hyperpolarization during an action potential. But if there's what we're going to call in just a minute called an inhibitory stimulus. And so something tells the cell to slow down, stop, whatever, we could just let fluoride ion move into the cell. The point is to acknowledge that not just potassium efflux can cause hyperpolarization. Also can fluoride ion. Is that okay? All right, what questions do you have about these terminologies before we put them to use? Let's now compare and contrast a graded from an action potential. We summarized these in lab last week, so let's just define them. What is a graded potential?
Under threshold.
It's a deviation away from rest, which is below threshold, sub-threshold. So a graded potential is a sub-threshold polarity change. Graded potential is a sub-threshold, that means below threshold change. Last week in lab, we talked about graded depolarization, where stimulus causes the cell to do what? Let a little bit of sodium in, but just not a whole bunch, right? Not enough to reach threshold. So a graded depolarization can be a stimulus that I can call it a weak stimulus. The presence of a weak stimulus may cause a nerve cell to depolarize, but not reach that cell's threshold. What we need to add here, though, is graded potentials may also be hyperpolarizing as well. So not only can a stimulus be excitatory and cause the cell to depolarize, but we can also have an inhibitory stimulus. We would call that a graded what? Hyperpolarization. You can also have a graded hyperpolarization of a cell. And during a graded hyperpolarization, that cell is polarity-wise in where in respect to rest? It's even further away, so the probability of generating action potential then is extremely unlikely, right? And so when there's a graded hyperpolarization, there's something inhibiting the nerve. Telling it to turn off, stop, slow down, whatever. At face value, that looks useless. I gave an example of some of you guys in the lab last week, right? Pain receptors, I guess. If you take pharmaceuticals or maybe you're having voluntary surgery or something like that, elective surgery or something, we certainly want to have our nerve cells inhibited, right? So one way we can inhibit them is to cause them to hyperpolarize. And the probability of them detecting that stimulus is less. So inhibition of nerves is okay. Excitation is definitely good, right? But we can also inhibit nerves by causing a hyperpolarization, graded hyperpolarization. We're going to elaborate a bit more on these graded potentials in just a moment, but I want to just contrast those to an action potential. How can we define an action potential?
Use a strong stimulus to go above the threshold.
Very good. Some strong stimulus a nerve cell, or you could say a target cell, to depolarize to the threshold. And there's some strong depolarizing stimulus that allows the cell to depolarize up to threshold. And action potential happens when a cell, nerve cell, depolarizes up to its threshold. Once it reaches threshold, which gates are opened on your nerve cell? Sodium. And what type of gate? Voltage gated. Sodium channel. So we'll grade up, however, the grade, the chemical, mechanical, thermal, whatever. We'll grade up whatever the stimulus is. And then once we reach threshold, at what part of the nerve cell are these voltage gated sodium channels open? The axon hillock. Probably at the axon hillock. We'll open up the voltage-gated sodium channels, and sodium moves into the cell, causing it to continue to depolarize. So we will reverse the polarity. Now it's really positive. Quick change in charge. And then we'll review all the other events of an active potential. Depolarization and repolarization and hyperpolarization. Before we move on, though, what questions do you have about some general comparisons between a graded potential and an action potential? Graded potential, weak stimulus. Could be a weak excitatory stimulus or a weak inhibitory stimulus. But an action potential is going to be a strong stimulus grading up the threshold. Yes? No. That's about the average. Minus 70 is an average. So not all cells have exactly minus 70. So it's relative. But it's about a total of about 100 millivolts total charge. Okay, so if it was at minus 70, it would grade up to 30. But if it was minus 75, maybe plus 25. So it's been, somebody's quantitated to a total of about 100 millivolts change. Good question. Additional questions? And these are the textbook averages, and these are what are accepted, so it's okay to be consistent with the 30. Yes? Is it bad to pass 30? Not that I know of. If it's regular, if a cell just, that's what its benchmark is, that's fine. If something unregulated just skyrockets and just for some reason the sodium channels aren't working or something like that, then yes. But each cell is going to have its own range. Okay, so let's think about a cell in your corpus callosum connecting your left and right hemispheres. It's always going to go from, say, minus 65 to plus 25. Always. Pretty consistently. It wouldn't go from minus 70 to plus 30 today, and minus 80 to plus 10 tomorrow, or whatever the case may be. So within a cell, it's going to be built pretty consistently. Does that make sense? I don't know what that is. I refer to it as the peak of action, or you can say the peak of depolarization. I've never looked up that term, so I just refer to the peak of the maximum depolarization. That's a good question. I don't know if there is a term for it.
I noticed in the book they call it the peak, they labeled the peak action potential.
They may have labeled that the action potential, but the whole thing is an action potential. The whole grading up to threshold, depolarization, repolarization, and hyperpolarization. So this whole plot is an action potential, not just the entire. So thank you for acknowledging that. So the question was, what about pain medicines? I thought they blocked the receptors. So there's different types of pain medicine. So some can block the receptors, the pain receptors, so that they never actually even depolarize. Some other things like, I think it's lidocaine. No, lidocaine blocks sodium channel. Other ones will open up chloride ion channel. So there's just so many many different chemicals. Some do block channels and some promote active inhibition. They may be called blockers or creators.
So what is anesthesia?
Well, anesthesia should sedate a nerve so that it doesn't depolarize to threshold. The question is, how does it work? Does it block a sodium channel or does it promote hyperpolarization? And so a lot of them do block the sodium channels. Some actually cause the cell to hyperpolarize.
So why do you not do that?
That one, so those gases, they suppress your, I don't know what part of the brain, but they suppress your nerve cells. And so if they're not, if you're awake, your nerve cells are active, and if you're awake, they're inactive. So they target specific central nervous areas so that they don't depolarize and send them forward. All right, good questions. Any other questions? So let's look at those graded potentials. I kind of described them a moment ago. The graded potentials that cause a cell, a nerve cell, to get closer to threshold are called excitatory postsynaptic potentials. And when I was preparing my Chapter 8 presentation, I was getting ahead of myself, so this is going to be covered in Chapter 8. If you're looking for this in your transcript. So an excitatory postsynaptic potential is a stimulus, chemical, mechanical, thermal, whatever, causes the cell to do what?
Closer to threshold.
By what polarity? Yes, it becomes closer to threshold by depolarization. So an excitatory stimulus, excitatory postsynaptic potential, is a graded depolarization. Just a graded depolarization. Due to which ion?
Sodium.
Sodium moving into the cell. So in this plot, where is an excitatory postsynaptic potential? The first two are the excitatory postsynaptic potentials. And they're two little graded depolarizations. So why don't you check your work on your handout that you're turning in today and see if we plotted something like this. What question is that? Number 1? Very good. What should you have shown here, though?
-7.
Well, rest and we're gonna have threshold represented. These depolarizations should be where in respect to your threshold? Below it. So a little speed bump, if you will. A little depolarization, but closer to threshold. So by itself, it looks really uneventful. Like, why are we talking about this? We'll tell you why in just a minute. So an excitatory postsynaptic potential occurs in the presence of an excitatory weak stimulus. It's a single graded depolarization, brings that cell a little bit closer to threshold, but doesn't cross it. Cause it to cross it. Or reach threshold. You okay with this? By contrast, we identified a nerve cell could be inhibited in the presence of an inhibitory stimulus by opening one of two types of channels. We could open up potassium or fluoride. Potassium would flow. It would flow out of the cell. If we open up fluoride channels, fluoride would flow, causing the cell to become more negative than it was at rest and even further below threshold. So how many inhibitory postsynaptic potentials are shown in this image? Just one, and the last one. So these are two types of graded potentials. One brings it closer to threshold, while the other brings the cell further away from threshold. One favors an action potential, one does not. One actually prevents an action potential. And when it applies, we'll inhibit the cell. Hopefully the burning question that you have is, well, if these are below threshold, what's the point of them? If they don't generate an action potential, why do they exist, and why are we talking about them? We're talking about them because graded potentials can be summed together. What does that mean? They can add up to reach threshold. So multiple graded potentials can be summed together to approach the cell's threshold. And then do what? Create an action potential. Or you could say fire. We'll call it an action potential. This will help if you put it in context a little bit. If we think of all the billions of cells in our brain and spinal cord alone, there's lots of interactions that may be going on at any given time inside of our body. And so in this image, I have a single large, what we're going to call postsynaptic cell, where you see the cell body in the background, little axon. We don't see the whole cell, but we see part of it. We can see the sensing end. But if you look at it, there's a bunch of other nerve cells synapsing on it. And the synapses are highlighted red and green. The synapses that are in red indicate what we'll call inhibitory synapses. Wherever that interaction is, this postsynaptic cell will do what? At that spot. It will
Inhibit.
And which direction would its polarity change at that site?
More negative.
More negative, or we would say hyperpolarized. The word I was fishing for is hyperpolarized. So whenever they appear, this nerve cell releases neurotransmitter. It's going to cause this second cell hyperpolarized at that spot. And wherever we see green, that's indicating an excitatory synapse. So wherever those little locations are, the second cell will do what? Depolarize. It may be just a graded potential. But if we start adding up, say, all of these plus all of these and these, this question is, well, what is the net polarity effect on the cell? Is it enough to cause that second cell, the postsynaptic cell, to reach threshold or not? In other words, we would have to sum them together. Does that make kind of sense? We take a hyperpolarization and a depolarization. Do they net enough to bring up the threshold or not? And what we're kind of looking at. So before I move on, I want to see if you're okay with the word sum. Summing graded potentials. I'm doing what with them? Adding graded depolarizations with maybe even graded hyperpolarizations to see if they collectively cause the postsynaptic cell to reach its threshold, which would then lead to an action potential. All right, so if we're okay with the term summation, we're going to look at the different types of summation. There are two broad categories of summation, including spatial and temporal summation. The first we're going to study is called temporal summation. That name, has anybody used that word before?
Time.
Like over time, right? In temporal summation, one presynaptic cell is going to release neurotransmitter quickly over a short period of time. Again, in temporal summation, the presynaptic cell is going to release excitatory neurotransmitter over a short period of time or a rapid period of time, right? It's just going to quickly release excitatory neurotransmitter, causing the postsynaptic cell to grade up to not quite the threshold, but before it completely goes back to rest, another excitatory neurotransmitter is released. So as it's getting closer to threshold, before it goes back to rest, we get another excitation. So you're kind of stair-stepping, if you will, adding binding together. But the key is, in temporal summation, it's one presynaptic nerve cell releasing neurotransmitter rapidly. In temporal summation, one presynaptic cell releasing excitatory neurotransmitter rapidly. So that when the first set of neurotransmitters are released, the cell depolarizes. Before it repolarizes, it gets another set of depolarization events. Eventually, it could sum up to threshold, which generates an action potential. Sum up to threshold, and then generate an action potential.
So that's like each step. You have the first one and then another. It's not the same.
In temporal summation, it would be one cell, one presynaptic cell releasing neurotransmitter rapidly, affecting what the term we'll call it the postsynaptic cell. Its polarity. This animation that I'm going to show may help you a little bit, but I just want to have your attention here real quick. I'm going to put little lightning bolts that are tiny to try to fit in here. So I just want to have just turn your attention to it. It'll happen, I think, pretty quickly. In temporal summation, can you see where the lightning bolts are or not? I try to put them in purple. All these little parts are from one presynaptic cell. Okay, so when the first cell generates an action potential, it releases neurotransmitter. We're saying, well, what's the effect on the cell receiving the stimulus? Watch the lightning bolts. Okay, so we're releasing neurotransmitter, brings that cell a little bit closer to threshold, and before it gets back, right, it depolarizes again. So it just continues like this isn't happening as good as I was hoping. So does it make sense? Can y'all see the flashing at all? Okay. So neurotransmitter release, cells a little bit closer to threshold, and then release more neurotransmitters. We're fighting across the threshold quickly because we're summing our depolarizations together. And so during temporal summation, let's say this cell releases some neurotransmitter. You normally just go right back. But before the cell can get back to a rest, more neurotransmitters. Stair-stepping, if you will. The key, the differentiation between temporal is it's one cell releasing neurotransmitter rapidly. So it's a postsynaptic cell can never fully get right back to rest before another excitatory stimulus comes. It's just like compounding together, building, or you would say summing the depolarization. To process threshold, which would then generate our characteristic action potential. Our graded temporal summations can sum to threshold to generate an action potential. I already stated that. So how many nerve cells contribute to temporal summation? One presynaptic cell excites the postsynaptic cell really quickly. But as we noticed in this image, there's lots of other inputs, and so we could sum multiple presynaptic inputs together by what type of summation? Spatial summation. I'm going to use the same flashy, tiny little lightning bolts, if you will, and put them across different areas. So we can see multiple presynaptic cells. Can you see the flashing image? So at the same time, multiple presynaptic inputs cause multiple graded potentials. We may have graded depolarizations and graded what? Hyperpolarizations at the same time. The question is there enough grade depolarization or not to cause the cell, postsynaptic cell, to reach its threshold?
So this is more than one cell.
More than one presynaptic cell, yes. In spatial summation, more than one presynaptic cell will release their neurotransmitter at the same time. In a spatial summation, more than one presynaptic cell will release their neurotransmitter so that their individual grades are summed together. Interesting enough, a depolarization may be outweighed by a hyperpolarization. So that the net effect is actually no change in the postsynaptic cell. So the depolarizations didn't outweigh the hyperpolarization. There's no net effect. But certainly they could sum together excitatory and bring the cell up to threshold. What questions do you have on the difference between spatial summation versus temporal summation? Or even just what summation is? What depolarization?
Temporal more,
in this case, in spatial summation, you can also grade up to threshold. In this example, we see it did not. But I could have just as well shown 5 excitatory presynaptic inputs depolarizing up the threshold really quickly. But in spatial summation, the excitatory neurotransmitter has to be released so frequently that they stack and quickly cross the threshold. So I think maybe your question is, does spatial summation always cause no effect at the postsynaptic cell? The answer is no. They can grade up to the threshold just as well as temporal summation. Is that where you were going? Spatial summation can depolarize up to threshold. We're just showing how they can also cancel each other's effects out. What other questions do you have? Is that the end of chapter 7? I'm running out of notes. Nope. Okay. I'm just messing up my pages then. Okay. All right. Certainly not. So gradient potentials are electrical changes below threshold. They can depolarize closer, hyperpolarize, and get further away. But the whole point is to reach threshold, whether it be by temporal or spatial summation. Once that happens, we can generate an action potential. And I want you to take this moment to plot an action potential. Plot and label. Voltage over time in millivolts versus milliseconds. Indicate your threshold voltage. If you want to sum, if you want to sum some grades together, that's fine. Or if you just want to have a single strong stimulus, that's fine too. your action potential is plotted and labeled, go ahead and include which ions are moving to which fluid during each phase. You can check your work. We should have something looking like this. We plotted our voltage over time and indicated are your rest and your first blue line and then your threshold voltage. We identified as well those specific voltages depend upon the cell type and species. It's kind of our benchmarks, if you will. Once a strong stimulus is received, the cell will depolarize up to threshold. Now, go ahead and mark on your grading up the threshold. That getting to threshold is due to whatever the stimulus is. Be it chemical, mechanical, thermal, or electrical. Getting to threshold is just due to whatever the stimulus is. Whether it be another neurotransmitter, or an ion, or temperature changes, whatever that cell is specialized to detect, right? Can bring it up to its threshold. So, we're going to highlight that. This first upward swing, boom, highlighted in yellow, is caused by whatever stimulus caused it to grade up. But once it approaches threshold, we open up what at the hillock? Voltage-gated sodium channels. We can open up the voltage-gated sodium channels, probably at the hillock, and then generate the rest of the action potential. This entire upward swing we would label depolarization. Due to which ion? Sodium moving into the cell. Very good. And then once we reach that maximal depolarization, those voltage-gated sodium channels do what? Close. And now what happens? Voltage-gated potassium channels open, causing potassium to move out of the cell. Polarity-wise, we would call this repolarization. Repolarization happens when our voltage-gated potassium channels open and potassium flows out of the cell, down its gradient, electrochemical gradient. We may have identified in lab that a period of what happens next? Hyperpolarization happens because the voltage-gated potassium channels don't close as quickly as our sodium ones did. So as the cell approaches rest, the potassium channels are still open. So potassium still leaks out, causing it to undershoot its rest. So we've labeled this purple swing hyperpolarization. As soon as we generate an action potential, we're going to regain what? Resting memory potential due to the leaky channels and the sodium potassium pump. questions you have about the phases of an action potential? This is a single little action potential. It's taken us a couple of weeks to even just get familiar with it. You guys are sounding more familiar, so I'm happy with the progress that we're making. And we're going to build from here. Because this is a one single little action potential that happens in one little microscopic part of the cell. And so we've got to conduct it down an axon, whether the cell is myelinate or not. But before we can conduct it, we need to understand the components of an action potential. If we were to look at an action potential a little bit better, we can also identify the role of refractory periods. Refractory period is another one of those generic words, but if we're looking at the refractory period of a nerve cell, there's two refractory periods, one called an absolute refractory period, and another one called a relative refractory period. We'll use these same terms in how the heart works, so don't think it's just exclusive to these cells. The point of a refractory period, basically, is to make sure that once an action potential is set in motion, then it continues and turns off. We want to deal with one action potential at a time. As you notice, it's kind of confusing by itself, right? Once it kind of rolls on itself, it gets really, really complex and nerves would work, basically. So again, the point of your refractory periods is to ensure that one action potential is handled before another is generated. So once a strong stimulus is received, we'll go through all the phases and get back to rest before we receive a new stimulus. Does that make sense? The rest is technicalities, absolute versus relative. Okay? During the absolute refractory period is when the cell's in the middle of depolarization. When our voltage-gated sodium channels are active, the probability of the cell receiving a new stimulus and crossing the threshold again is pretty minimal because we've already activated the sodium channel, the voltage-gated sodium channel. They're busy. They can't continue to be activated. They're already working. Does that make sense? It's already open. They're already doing their thing. So the probability of keeping them open longer than necessary, maybe like what Scott was asking, well, can we even overshoot that 30? The probability is very minimal, almost none, because they're already activated. They're set in motion. So that's the absolute refractory period, when the voltage-gated sodium channels are activated. After they shut, we open up the voltage-gated potassium channels. And when the voltage-gated potassium channels are open, we're regaining what? We're regaining potential, we're regaining resting membrane potential, and we actually even hyperpolarize. You remember, hyperpolarization causes the cell to be really far away from threshold. And so in the middle of the relative refractory period, the cell is probably hyperpolarized. And even if a stimulatory event happened, the probability of it spontaneously depolarizing the threshold in that moment is very small. Right? So it's not going to happen. So that ensures the cell goes back to resting membrane potential. So again, the refractory periods just ensure that one action potential is handled and the cell gets back to rest before it generates another. So can our action potentials be summed? No. Action potentials cannot be summed. But what can be? Graded potentials. So another way to say this is these refractory periods prevent the summation of action potentials. So the terms which we've introduced today include the graded depolarizations and the graded hyperpolarizations. We've also reviewed the components of an action potential and then added the role of the refractory periods. What we're going to now look is go back and look at the role of the myelin and how it helps the conduction of an action potential. This next statement is a review from our lab from last week. We learned that not all nerve cells conduct at the same rate because they're not all built the same. Even in our body, not all cells are built the same. Okay? I mean, the most obvious examples that we've been using this semester is like the sciatic nerve, right? It's clearly much longer and built differently than, say, a nerve cell in your corpus callosum or your pituitary gland, for example. We learned that not all cells have the exact same diameter. And what correlation did we learn about the diameter? Larger, thicker, nerves conduct faster. We said there's a direct relationship between the size of the nerve and how well it conducts.
So it's like copper.
Like a copper wire, yes, like an electrical wire, or any conductive something. The larger the wire, the larger the nerve, the more conductive it is, or the easier it moves those ions. But we also learned that some cells have myelin and some do not. Those cells that do not have myelin, the type of conduction is called contiguous. Your book doesn't use that word. Your book just says nerve cells without myelin or something like that. A common word that is used is called contiguous. So if I talk about contiguous conduction, I'm talking about generating an action potential along a cell that has no myelin, a non-insulated nerve cell. By contrast, those nerve cells which are myelinated, the name for the conduction is called saltatory conduction. We're going to compare and contrast those. If we were to look at contiguous conduction in a nerve cell that does not have myelin, an action potential is, are you okay with the word conducted? What does that mean?
You said conduction.
Yes, if I'm conducting something,
Moving electricity along something.
I'm moving it, I'm coordinating it. Okay, in this case, we're flowing electrons. An action potential that we just described is not like a flash point on the whole cell. So you won't just see it like magically happening all across the whole cell at one time. It actually flows, as the term the current means. Okay? It flows from one spot of the cell to another. So basically, each segment of the cell generates its own action potential. And then the adjacent segment generates an action potential. And then adjacent. And the analogy that we had on Tuesday in class was someone, was that like the wave in a sports stadium? And that's exactly it. If you can envision like doing the wave in a sporting event, right? Someone standing up would be like the depolarization. And as they repolarize, the next section could depolarize. Okay? So instead of, right, don't take that, get it all the way. It flows along progressively. So each section of the membrane depolarizes to threshold and then repolarizes and hyperpolarizes. And then the next membrane would depolarize, right? Section of the membrane, all within one cell. As kind of implied in this image, right? So if we're looking at a tiny little microscopic part of the cell, zooming in, depolarization is indicated by blue, resting membrane potential by yellow, and hyperpolarization by which color? Red. So when a strong stimulus is met, at the hillock, we open up the voltage-gated sodium channel to let sodium in. And then sodium flows into the cell, and it happens to open up voltage-gated channels right next door, which lets more sodium in. So that section of the membrane would then cross its threshold, which happens to let more sodium in. So the next section of the membrane can, what word did I use to say? The next section of the membrane could depolarize the threshold, which lets more sodium in, which causes voltage-gated channels in the next section of the membrane to open up. Here's the catch, though. The action potential goes in one direction. Why doesn't it go backwards?
Because it doesn't need to.
But it doesn't know.
It's not that kind of cell.
Refractory period.
Because of our refractory period. The previous section was hyperpolarizing. It's not going to repolarize the threshold. So it's got to complete hyperpolarization. So even though sodium ions are coming in, maybe might want to open up the gated channels, they just aren't going to have impact to allow the cell, that section of the membrane to depolarize. So it progresses in one direction. And that's the role, remember, we said the refractory phase is to prevent a section of membrane from going spontaneously back up. So it just progresses back down. And by the time the active potential gets far enough around, that other section was back at rest. So it's basically not going to be effective.
Is this anywhere?
You have a similar image in your textbook. This will be in chapter 8. I think, no, this is in chapter 7. I'll look it up and just, what page is that, Brandy? Page 189. I didn't use that image because it's really just busy. But I like to do it.
Now, just curious, what's the size of one of these sections? Is it like a micron, you think?
Less than a micron would be in the nanometer range. So it's tiny. The actual measurement, I don't know, is microscopic. Submicroscopic. So in contiguous conduction, one section of the membrane generates an active potential, goes back to rest, and then the next rate of progresses from the hillock towards the terminal. We'll pick up what happens at the terminals in chapter 8. But there's no myelin here, and so we would call this contiguous conduction. By contrast, some nerve cells are myelinated, so the entire axon is not leaky to the membrane. You always have leak channels everywhere, right? But those cells that are myelinated are insulated because they have oligodendrocytes or Schwann cells covering up part of the membrane. Actually, the bulk of the membrane is exposed. So that only small segments of the axon have to maintain rest and leak and all that business and have our gated channels. So we concentrate the machinery for the action potential in segments of the cell membrane. So that once an action potential is initiated, and ions flow inside the core of the cell, inside the intracellular fluid, sodium can open up gates that are further distance down. So I don't have to have, we go back to that sports analogy, we don't have to have the entire stadium generating an action potential, just say maybe there's an odd section. And so as soon as section 1 depolarizes, it begins to repolarize section 3 to depolarize. So section 2 doesn't have to do any work. You go 1, 3, 5, right? So it's, what's the advantage? We said what? Faster. The mechanics are exactly the same, but we're just decreasing the surface area where all the work has to take place. So it enhances how quickly the actual potential gets from point A to point B. And we'll refer to this as saltatory conduction. The cells that are myelinated operate by saltatory conduction. What questions do you have over our Chapter 7 content before we get to our Chapter 8 content?